Okay, good afternoon, everybody. Okay, we come to the last section of chapter 16, the circuit arrangements. Okay, previously we have talked about parallel and series arrangement. So now what we are going to do is we'll look at one or two examples to see how the arrangements will actually affect your calculations and how you should adopt, how you should go ahead to analyze the circuit before solving the question itself. Now, let's see. Okay, come. Now, resistors in series and parallel. Okay, although the title says resistor in series and parallel, but we will also be looking at how potential difference, how current works in series and parallel. If basically what we are trying to say is that I'm going to combine these two, okay, into different examples. Okay, because in real life we will not get a pure series or pure parallel circuit every time. So you will be dealing with a mixture circuit, a composite circuit, like we say. Now, what happens is when you have a composite circuit first, okay? When we have a composite circuit, what do I mean by composite circuit? Okay, give me a minute first, huh? Okay, what do I mean by composite circuit? Whereby you see that there are three resistor here. You'll find that if I look at 3 ohm here and 4 ohm here, okay, they seems to be side by side, but they seems to be in series arrangement. But they doesn't look like the series arrangement that you usually deal with. For example, if it's a series arrangement that you see in the previous video, it will look something like this. They are side by side, one path for the whole entire, one current path for the whole entire resistors. But you find there is a bit of missing gap here. There seems to be a split path here. Okay, there seems to be a split path here. So between 3 and 4 doesn't seem to be like a complete series circuit. So for students, right, if you have this type of doubts, whereby the resistors you are not sure whether they are series or parallel, my advice is don't do that arrangement yet. Look at other arrangement. For example, this. For example, you look at the arrangement here. Okay, so you look at the arrangement here. So 3 and 4, you can't be sure whether they are series or parallel, so don't touch first. So what about 3 and 6? 3 and 6 arrangements, okay, whereby the resistors are connected up and down. The path seems to be split up. So you can see that it looks like a normal parallel arrangement. You see the current will come in and my current will split up and down. And you'll find that my current will actually flow up to the 3 ohm resistor and it will flow down to the 6 ohm resistor. It looks like a standard parallel arrangements like this in the previous video here. So if you are sure that this is a parallel arrangement, okay, then my advice is you are safe to go ahead to manipulate the resistor, for example, merging them together. Okay, so the trick here about finding effective resistors, about merging the resistor is the first rule that I always tell myself is if I look at the resistor, and I can't be 100% sure of the arrangement, they are like a bit series, a bit parallel. If I have this type of doubt, which means that particular set of resistor, I will not want to touch it. I will not want to merge it because it might have a bit of ambiguity. So rather than that, I will actually look at the arrangements that I am sure that they are 100% series, 100% parallel. Then I will merge that particular path here. In this case, I will know that 3 and 6 are parallel, 100%. I'm very sure. But they look like the previous examples that I've seen in my previous few videos for parallel arrangements. So what I now do, I will adopt the parallel arrangement formula, reciprocal of everything, merge them together. So then after that, I'll add them together. So 1 over 3 and 1 over 6, I'll add up, it will become half. But remember, this is only RP. 1 over RP is half. I have not find the parallel resistor yet. I need to do one more step, flip it up. So after flipping, I'll know the parallel arrangement will be 2 ohms. So what I have done now is actually I merge the 3 ohm resistor and the 6 ohm resistor. Because they are in parallel, I merge them together. So when I merge them together, they become a single resistor, which is something like this, the 2 ohm here. So now, after merging, you will find that the 3 and 6 ohm will disappear to give you a RP here, which is a 2 ohm resistor. And now you'll find that RP connected beside the 4 ohm. These two, they are connected and the current going through them in a single path and they're connected side by side, I will know that 2 ohms and 4 ohms now, they are in series. So what I do now, again, I will combine the two resistors together. And because I know they are in series, I will adopt the series formula for resistance. I'll add them together. 4 and 6, I'll add them together and I'll get an effective resistor of 6 ohm. So now what I do is I added the resistance again, but now I added them in terms of series. So what I do now, after adding, I'll get 6 ohm. So what I'm trying to do now is I'm merging the 2 ohm and 4 ohm together to become a single resistance. So what I have done now is I merge them into a single resistor. So from the very beginning, I began with 3 resistors arranged in some combo or mixture arrangements. So what I do at the beginning is I identify the resistors first. Which resistors, which pair of resistors or which set of resistors is 100% in parallel or in series. Once I'm sure, I add them. In this case, I'm sure this is 3 and 6 and the resistor 3 and 6 is in parallel. So what I do then is I add them first. So I add this first in parallel arrangements. After that, I know they are in series. I add them again or I simplify them again using series arrangements. So you'll find that the effective resistance of this particular circuit, I have effectively reduced this circuit from using a 3 resistors to a single resistors. Okay. And I've managed to shrunk 3 ohm, 4 ohm, 6 ohm into a single resistor of worth 6 ohm worth. Okay, and to do that, I actually took on multiple steps, multiple math. Okay, and this is what we expect the students to be able to do to simplify the circuits through recognize it as a series arrangement or a parallel arrangement. And this circuit is what I call a combo circuit. So students, you must be aware that not all the circuits that are given to you or not all the circuits in the world are pure series and pure parallel. In fact, none. Okay, usually it's combo circuits. Okay, so same thing now, the next arrangements. Okay, the next circuit I have here, I have a 3, 4, 6 ohm resistor arranged weirdly together. Okay, so now you have to identify the set. Okay, to simplify them into a single resistor, what you need to do is identify the set of resistors that you are very sure they are in series or they are very sure they are in parallel. So what I do now is let's analyze. Okay, if I look at 3 and 6, there seems to be an up-down arrangement, seems to be like there's a bit of splitting. But the arrangement is a bit off, a bit different from the usual parallel arrangement. Let's recall the parallel arrangement that I showed you previously is this. One resistor up, one resistor down. That's all only. Okay, so the current will split up, split down. After that, they will merge back again. So this is what we mean by a parallel arrangement. One resistor on top, one resistor below. But right now, if you look at 3 and 6 ohm, yes, they are one resistor up, one resistor down. The path flow through 3 and current flow through 3 and flow through 6 ohm, yes. But somehow there is a 4 ohm on the right side here, which is a bit different from here. So I'm not very sure or not very convinced that 3 and 6 ohm are purely in parallel arrangement. So like I mentioned before, once you have these doubts, you do not go ahead to simplify the resistors. Do not go ahead to simplify to add up 3 and 6 using parallel arrangement because there is doubts. So which means the circuit might not be a pure, this 3 and 6 ohm might not be a pure series or might not be a pure parallel arrangement. So you need to go on to look at other arrangements, other set of resistors. So now let's look at 3 and 4. You look at 3 and 4, 3 and ohms and 4 ohm resistors, they seem to be side by side. And if you compare side by side series arrangement, it should look something like this. Shucks, give me a minute. Okay, if it's a series arrangement, it should look something like this. Okay, side by side. Okay, so if you compare your 3 ohm and 4 ohms and compare to this arrangement that you see in the previous video, you find that, yes, I'm very sure these 3 ohm and 4 ohm are series arrangement because they look exactly the same and they have the same property, one path follow through or one path for the current to flow through, the single path, single current. So if I know they're 100% series, I will go ahead and sum up 3 ohm and 4 ohm. And this is what I did. Okay, I sum up 3 ohm and 4 ohm because knowing that they are 100% series arrangement. So now after summing up, I will have a 7 ohm resistance. So which means 3 ohm and 4 ohm, I effectively combine them together to become a single resistor, which looks like this now. Okay, so now I'm slowly simplifying the circuit. So now same thing back again, I need to check what arrangement 7 and 6 ohm have. Okay, so one look, you'll know that they look exactly like the parallel arrangements that I mentioned in the previous video. So I will know that 7 and 6 ohm are parallel in arrangement, and I will activate my parallel arrangement formula. Okay, so it will be a reciprocate of individual resistor, add them together. So you have 1 over 7 plus 1 over 6, remember? Okay, this answer here is not the answer you want because this is refer to 1 over RT. I still need to flip it up because eventually I want RT. So I still need to flip up to become 42 over 13, and I simplify using my calculator, you get 3 over 2. 3.2. So what I have effectively done is I have effectively sum up 7 and 6 ohm together, merge them into a single resistor, which consists of 3.2 ohms. So in summary, what I have just done is I have actually simplified the circuits, the arrangements, okay, and to become from 3 resistors to become a single resistor. Same thing like the previous example. Remember, when you analyze a circuit, when you are simplifying the resistance, merging them, the rule of thumb is you can only go ahead with the adding if you are sure that the sets of resistor is series or parallel. If you have ambiguity, okay, don't go ahead. Look at other set of resistors. Okay, it could be that this set of resistor, like what I mentioned, 3 and 6, it could be a bit ambiguous, so don't go ahead. Okay, look at other set first. Do other set first. Maybe after you merge, maybe the first set, the arrangement will be more obvious. You'll be able to identify is 100% series or 100% parallel. Okay. So for merging of resistors, okay, you need a few practice, not just these two examples. You still need some practices. You can usually find these questions in the textbook, or you can look for your teachers to look for more questions to try out. But this arrangement, this analysis, you can only be better if you actually try, practice. Then you'll get a hang of it and you can do it quite fast. Now, so what happened after that? Okay, when you look at series, analyzing resistance, merging them, okay, what you are doing is you're actually trying to see whether you can look up other characteristics, like maybe the current in the circuit or the potential difference at certain components, and you can even find out the potential difference of maybe unknown resistor, like this example here. Okay, before solving, right, the first thing to look at is to look at the circuit first. Okay, analyze the circuit. Okay, so now you know that 2 ohms and 3 ohms here, they are side by side. You know that 2 ohms and 3 ohms, they are series. Okay, so I know 2 ohms and 3 ohms are series. 1 ohm and R ohms, they are in series. So once you know they are series, you know the certain properties. So I will know that the current through the 2 ohms and 3 ohms, the current will be the same. That's why I label it Ix. Okay, so because you know they are series, you will know that they will follow series properties. Okay, so what you do now is analyze the circuit first before looking at the math. So I know 2 and 3 ohms, they are series. And because they are series, a few things I will know. Okay, so let's say we analyze the circuit. So for under 2 ohm and 3 ohm, I will know that the current here, oops, sorry about this. So let me erase it first. So I will know that because they are in series, the current at 2 ohms going through 2 ohms and the current going through 3 ohms, okay, they are actually the same. Okay, I call it Ix. Oh, shucks. Okay, so sorry about it. Okay, so this, let's say Ix. Okay, so same thing, because I know 1 ohm and R ohm, they are in series also. So I will know that this current is actually the same as this current. So the 0.2 amp will actually be here also. Now, things to take note is Ix equal to 0.2 ohm? Is these two current the same or not same? We don't know. Leave it to the math. The math will actually tell us. Okay, and I also know that because they are in series, 1 ohm and R ohm, 2 ohm and 3 ohm, they are in series with each other. The potential difference across V2 here, if I add up the potential difference here, I will have one relationship whereby V3, V2, and V3 will actually be equal to the potential difference of the EMF. Why? Because if you look at potential difference across 2 ohm and 3 ohm, it's across this point. Okay, so let's say I give this maybe B and A. So you'll find that V2 and V3, right, the potential difference because 2 and 3, it can be V2 plus V3. It's actually across point A and point B. Okay, so which means that the potential difference of the EMF, 3 volts, is also across A and B. So which means that V2 and V3 will actually command the total voltage of 3 volts here. Okay, so this is what we mean by series property. If you know V2 and V3, because I know they are in series. So what I do now is I look, if they are series, they will have certain properties. Like example, current will be the same. Potential difference of 2, V2 and V3, if I add up, it will become the potential difference of the EMF itself. So this is what I mean by you analyze a circuit to look out for different properties so they can solve your question. Okay, now let's look at the solving. Determine the current I1. Like I mentioned before, because I know how do I find current, I can use back the formula R equal to V over I, which means that current is V over R. Okay, and I know the potential difference across 2 and 3 is actually 3 volts. So the total resistance across the junction, if they are in series, I will know is 2 plus 3. Okay, so total voltage, the potential difference, and the resistance, which is this formula. Okay, and you'll find that it will be 0.6. And because I know I2, your I2, the IX, okay, and the 0.2 ohm, there are two branches up and down. So which means the current in these two branches will add up to become I1. Okay, so that's why I know. Why do I do this? Because I know IX and 0.2 ohm M. These two current in the two branch, they are parallel branch. So within these two current add up will become the current in the main branch, which is I1. So I know the answer will be 0.8. Okay, this is how I use parallel properties, how I use series properties to actually help me solve in my mathematics. Okay, not just by using math brute force. I need to know what are the properties first before I use the math to help me. So now what happens is, how do I find the voltage at X and Y? Okay, so what I do is I need to find the potential difference across the 2 ohm first. Across the 2 ohm, same thing, R equal to V over I, or I can use V equal IR, which is Ohm's law. If I want to find 2 ohm voltage across 2 ohm, V2, okay, I need to know the current flowing through 2 ohms. I need to know the resistance of 2 ohms. Okay, so I know them, which is 0.6, like I mentioned in the previous previous part. And I know the resistance is 2 ohm. So I know V2 ohm is 1.2 ohms already. So how about V1? If I want to find V1, I will find V1. I will need to know I and R again. I will need to know the current in flowing through R1. I will need to know the resistance of R1, which I know. Based on the question, current flowing through I1 here is a current flowing through 1 ohm is actually I1, 0.2. Resistance 1 ohm. So I will get 0.2 straight away. So how do I find the potential difference between X and Y? I'll just minus the two of them. Okay, I will not go into detail of how I get into it. Okay, for those who are interested, okay, you can look up leave a comment below. I'll make another video or another updates for this particular section. If not, you can look for me when in class, or you can look for a physics teacher, to look at the details of how do I get X, Y. How do I get this answer here? Okay, but in a nutshell, how do I know X and Y? I'll just take the difference between V1 and V2, 2 ohms and 1 ohms, the difference between the voltage here and the voltage here. I'll take the difference between them. I will know, I will be able to get the potential difference across X and Y. Okay. Now, how do I find the resistance across? How do I find the resistance of this resistor here? The easiest one I will know that is I use series property, because I know V1 and VR, they are in series. Okay, V1 and VR, they are series, which means that some of the resistor, some of the potential difference will be actually equal to the potential difference across it, which happens to be the EMF voltage here, which happens to be 3 volts. Okay, so 3 volts here, it happens, how do I know it's 3 volts? Because it happens to be the EMF of the circuit here. Okay, like I mentioned before, this is VA, this is VB. Okay, so this V1 plus VR is potential difference across A and B. And it happens that the EMF is also across A and B. So that's why I know that potential difference across A and B is the potential difference of the EMF, which is 3 volts. And because of this, I know VR, okay, will be 2.8, because I know V1 is 0.2 volts. How do I know V1 is 0.2 volts? Simple. Okay, V1 is I1 plus R1, okay, which is here. Okay, I1 is 0.2, R1 is 1 ohms. I will get my answer to be 0.2 volts. Once I know the voltage of R, potential difference of R, which is 2.8 here, what I do now is I go back to the basic formula, R equal to V over I again. Okay, so I substitute the voltage, I substitute the current flowing through the resistance R, I'll get my answer to be 14 ohms. Okay, this is how I use the math to aid in my calculation for the circuits. But to use the math effectively, you need to understand the properties of series and parallel arrangement and use them effectively in your calculations. Okay, and similarly, the properties of series and parallel is like what I mentioned here. There are a few things in series: the current, the voltage, and the resistance. They are different. Okay, if I put them side by side, you'll find that for parallel, voltage, and resistance, the breakdown is the same, whether it's series or parallel arrangement. The breakdown in the sense that series and parallel arrangement, you look at how the current behave, the potential difference behave, and how the resistance behave. But individually, okay, for series arrangement, the behavior of current is different from the behavior of current in a parallel branch. So as a student, you need to understand how the properties of each of them works, how the current voltage resistance in a series differ from current voltage resistance in a parallel branch. So you need to actually know the properties at the back of our mind to understand how I get them. Then after that, you use this property to analyze your circuit, so that you actually knows how to solve it, and then you can use the math to solve it. And this cannot be done like easily across like 1 or 2 examples. So you literally need to look at the other examples in your workbook or textbook or even your notes to practice these properties, to use it effectively, fast, and effectively to solve the questions. Okay, if anything, okay, you can refer back to your teachers or books. Okay, if not, if you have questions, you can leave the questions at the comments below. I will get back to you ASAP. And if not, okay, remember to subscribe to my channel to get the latest update for the upcoming topics, or the notes or the explanation for various topics. Okay, if not, see you and have a nice day.